what do I do? I'm the head of mobility research and assessment team at Kaspersky SSR. Our team performs a security audit of hardware and software products used in industrial control systems, transportation, telecom industry, and we hope to find visible vulnerabilities and fix them. Over the past 9 years, our team discovered, reported, and in some cases helped to fix several hundred vulnerabilities across a large number of different vendors. Some of the vendors are presented on this slide. This story will be about the results of the security assessment project against an internet-facing systems of one automaker. Spoiler. I will tell you a real-life story how a single vulnerability in a contractor's web application can lead to a complete compromise of tens of thousands of vehicles. During the project, we played the role of an external attacker without any special knowledge of the system. As an attack surface, we had a set of internet-facing systems of the automaker, and also we had direct access to the vehicle, and we knew it sends some data to the cloud. During the stage where we were gathering additional information and validating the list of target hosts with the customer, a couple of very interesting web services was discovered. These web services were located in the contractor's infrastructure, but their DNS names belonged to the automaker's DNS zone. So the customer decided to include these applications to the scope of the project, and one of the web service was a wiki application, and the another was an issue operating system. During the assessment, our team discovered a zero-day vulnerability in the wiki application. It was a common SQL injection. But the research process was quite funny. When we studied the product documentation, we found a way to search for objects from the database using the internal query language. This API could be accessed without authentication, the example of search query from the documentation looked like a classic task of capture the flag repetition. Hey, this is the vulnerable piece of code, please try to hack it. Okay, we tried, and of course we hacked it. This is the example of our POC, proof of concept script. This is a search query that exploits time-based SQL injection. The trickiest part was to break out of the Hibernate query language context, and the way we do it will describe it in many published research papers and blog posts. Using the vulnerability we discovered, we read from the database the password hash of the built-in administrator account and got the administrative access to the database when we forced the password. After that, we used built-in functionality of the product of the wiki application and installed a specific plugin to run shell commands on the server. In fact, at that moment, we realized that we had access to the contractor's corporate network. Being in control over the network of contractor was beyond the scope of our project, obviously, so we just limited ourselves in getting a list of users with the password hashes from the server of the wiki server. As a result of the root force attack, we gained several passwords for several wiki users. And after that, we tried to use these passwords to get access to another service, the issue tracking system. The password for one account was the same, it was correct, and we gained access, user access to the issue tracking system. As a result of that, we gained access to a large amount of information about the automaker's infrastructure. For example, in the attachments to one of the issues, we found a zip file of the GC directory. This zip file was created on some server belonging to the telematics infrastructure of the automaker, and a part of etc shadow file was included in this zip file. The etc shadow file is a specific file in Linux operating system that contains password hashes of system users. As a result of the brute force attack on these hashes, we got passwords for several accounts on this server. But we didn't have access to the telematics infrastructure to use these passwords. Next, we proceeded to a security audit of the vehicle's telematics control unit. This unit collects data from the vehicle and sends it to the cloud. This cloud named telematics infrastructure on the slide. A GSM modem is used for data transmission, and the access to the telematics infrastructure is permitted only for certain SIM cards. Since we had a telematics control unit with a suitable SIM card, we have network access to the telematics infrastructure. And we started exploring available services and immediately discovered that the network diagram on the slide differed from the actual network configuration. It turned out that the firewall was configured incorrectly and it worked actually as a router. So we had network access to all internal servers of the telematics infrastructure. Since we have this type of access, the next step was to identify the servers to which the file we found in the issue tracker belonged. And these servers turned out to be free LDAP servers. After that, we tried to use the password we guessed from the etc shadow file to access to these servers. The zip file in which we found the hashes was quite old, and the passwords for most of the accounts had already changed. However, the password for a cluster service account worked. This account was used to join multiple servers into the cluster, but unfortunately we were unable to use this account to log in interactively via SSH. However, judging by the error message, the password was correct. And the reason we couldn't log in interactively via SSH was because the shell for this account was specified as vNoLogin. vNoLogin is a specifically designed shell to disable shell access and produce output complaining you can't log in. This fact, of course, upset us, but we continued to explore the infrastructure to find some way to somehow get access to some server. And during the network scanning, it was discovered that Zabbix monitoring system was used to track availability and performance of the servers. This monitoring system is designed as follows. There is a specific Zabbix agent installed on each server, and Zabbix server connects to the agent and requests for required metrics. To restrict network access to the agent, a list of IP addresses that are allowed to connect to the agent was specified in the configuration file of the agent using the server active option.
By default, this list of API addresses includes local requests are usually allowed. And it is also important to note that the Zinenko again was run with administrative privileges. The allow root option was responsible for this. That we used a cluster account not for interactive or media SSH, but to create an SSH tunnel to the TCP port of the Zinenko again. Through this tunnel, we send commands remotely to the Zinenko again, but we thought that requests were running locally and allowed them. Thanks to this, we got the ability to read arbitrary files from real-time servers via Zinenko protocol.
Then we examined content of the server. We found in the command history of one user a mistakenly entered password. It later turned out that it was password of account of now a contractor, and this account was privileged, and it was present on all servers with the same password. Using this account, we gained control over the entire telematics infrastructure. And next, we studied interaction between the telematics control unit and the telematics infrastructure. It turned out that the telematics control unit connects via MQTT to a specific topic and waits for command. We found that the command list includes a specific command to update the firmware. When we analyzed the firmware, we discovered that the telematics control unit didn't check the signature of firmware. Thanks to this, we got the ability to modify firmware in any way we wanted. After that, we began to figure out where it was possible to affect the safety of the vehicle by controlling the telematics control unit. And it turns out that it was possible. In the vehicle, we elevated a central gateway, which acts as a firewall in the vehicle, allowed access from the telematics CAN to the powertrain CAN, where the transmission control module or engine control module were located. This discovery allowed us to gain control over all connected vehicles and affect the safety of the driver and the passengers. By the way, when we had already gone through all the steps that I talked about before, we found another way to achieve the same results much simpler. We found a zero-day vulnerability in firmware over air portal. This is the application to manage and deploy firmware updates for connected vehicles. As a result, we found a vulnerability to bypass authentication process, got the administrative access to this portal, and after that we got the ability to upload modified firmware for telematics control unit using very user-friendly web interface. In conclusion, let's go over weaknesses we discovered during the audit. The first problem discovered was that a couple of web services were accessible from the internet. Then we use weak user password, and because there was a lack of two-factor authentication, we could access to the issue tracking system. The fact that the contractor stores confidential information in plain text allowed us to get password for hard cluster user.
Due to the lack of network access restrictions and the use the default settings for SSH and for statics again, we can get a password for privileged user. And because this password was the same on all servers and password authentication in SSH was enabled, we were able to gain control over all telematics infrastructure. And lastly, the lack of firmware signature verification in telematics control unit allowed us to affect the safety of connected vehicles. And based on the results of the security audit, we recommended that the contractor and the automaker should implement several hardenings. By the way, most of the hardenings have been already implemented. First, we recommended that contractor should limit access to the big application and each system from the Internet of Things and use VPN to access to them. Next, for the automaker, we recommended to restrict access to internal services from the vehicle network segment. Next, we recommended improving network isolation. We recommended to the contractor to isolate public services from the corporate network. And for the car manufacturer, we recommended restrict communications between internal servers based on allowing. We also recommended improving existing password policy, so to force users to use more complex passwords. To detect the development attack in a timely manner, we recommended to organize collection and transmission of security events available to the CN system and to analyze them. Also, we recommended the contractor implement factor authentication of big application and issue tracking system and stop storing sensitive information in plain text. And for the automaker, we recommended to disable password authentication in SSH and disable SSH forwarding feature. Prevent applications from being running as super user and implement signature verification for 4 months and for the firmware to check how So that's all, and it's time for questions.